Today we are going to look at finite automata. A finite automaton is also called a finite machine, which can be viewed as a state diagram. So first let's look at what a state diagram is. A state diagram is a directed graph. And also the nodes and edges are both labeled. Okay, you have labeled nodes and also you have labeled edges. And we use a node to represent a memory state. Okay, so as you can see here, the memory is limited. We can only store some information on the node. And then the edges are also labeled that cause movement between states. Okay, so depending on which state or which node you are in, and depending on what input you receive, then you decide where will the next move, will be. Okay, in other words, where the next state is going to be. So now let's look at a simple example of the state diagram. So let's consider an electronic sensed door. Okay, so if you don't look at the sensing devices, just look at the control mechanism behind the sensor door. We can view this. We can view a sensed door as a two-state diagram, okay, or two-state finite automaton. So it has two states. That remembers two status, okay, the door, if the door is closed or if the door is open. Okay, so let me draw a diagram here. So let's say this door, we have a door. This is only, suppose this door is open only when there is a customer wants to go in. Okay, so let's call the outside as front. Okay, so it only opens automatically when there is a person wants to go inside, and this is behind the door. So this is behind. Behind the door. Okay, so and the door either remains closed or is going to open or remains open. So there's two states, right? So that's for the door. And then there are four inputs for the door. Okay, so which means a person could be coming in. A person could be coming in from the outside, want to go to the other side, or a person's near this door, but the person, of course, this door cannot open if the person is behind the door. So this is only open for customers from outside, customer who want to get into this door. Okay, so now we want to know how to determine whether this door is closed, whether the door should be opened, depending on the situations of persons in front or behind. Okay, so let's assume the door is closed at the beginning. And then if there is a person in front, okay, then this door will open. So that means, suppose the door is closed and then it sends someone coming in then it's going to open the door for that person. Okay, so that is this move. And then if there is no person from outside, but there is a person behind the door, then it remains closed. Okay, so behind, I mean, it remains closed. So where? And if there is a person behind, and there's also a person in front, it's also remain closed, because in this situation, you don't want to open the door. Okay, so only when there is no person behind the door and there is a person in front of the door, you open that door. The door will open. And if there are no people on either side, of course, it will remain closed. The door remains closed. Okay, so that is in this state. So once you have a person in front and there is no person in the rear, then of course the door open, the door will move to this state. And then if after this door is open and there is a person in front coming in, or there's a person behind, or there are people on both sides, then you should remain open. Okay, and otherwise, then it's closed. Okay, so this is for security. This is for safety reason, because once the door is opened, you have a person in front, then you should let that person coming in, so the door remains open. If there is no person in front, but there is a person behind the door, you don't want to close the door because the person may bump into that door, so it should remain open. Similarly, if both sides have people, then it should remain open. If there are no people on either side, then you will go to close. So the door will go to this place, go to this state, and go to this, the door will close, okay? So this is a state diagram. So now let's formalize this state diagram, and we define what a finite automaton is. Okay, so first let's define what a alphabet is. Okay, so the inputs of a state diagram form an alphabet. Okay, in our previous example, we have 4 inputs, so that's our alphabet. And then a movement from one state to another is a transition. Okay, so you are on a current state, and then you have an input, and that movement is a transition from one state to the other, or remains the same state, right? So it's a transition. In addition, we may also specify an initial state, just like the example we look at. We assume at the beginning, the door is closed. So that is an initial state. And we can also, because now we want to define computability, so we want to determine when an input is accepted. So then we define a set of final states, also called accept states, okay, also known as accept states. So once we have this, then now we can formally define what a finite automaton is. So an FAM is a 5-tuple Q, sigma, delta, Q0, and F, where Q is a finite set of states. Okay, so this, you can think of this as our memory, which are the nodes in a state diagram. It's labeled. And big sigma is an alphabet. Okay, so this is for inputs. It is also a finite set. Small delta is a transition function, which maps a state and an input to a state, to either a new state or it remains in the same state. So it is called a transition function. Okay, so in other words, you can write it as delta. Let's say I am on a current state Q. Okay, Q. Let's say my input is A, and it goes to a state P. So P could either be a new state or P could be Q. So in other words, if we look at a state diagram, this is Q. Let's say my input is A, which is an alphabet, and I go to P. So when P is not equal to Q, if P is equal to Q, then it will go like this. Okay, so this is when P is equal to Q. So that's a transition function. All right, and then we designate a initial state, so that's Q0, and then we designate a final set of states as accept states. Okay, so we normally use the following notations as a Q0 to indicate it is an initial state. So this is at the beginning. And for the final state, we use a double circle. Let's say this is a final state or accept state. So it is a state diagram, but now it has an initial state. It has a set of accept states. You have a transition, so this is the state diagram as we get before. And that is a finite automaton. Okay, so now let's define what we mean by accepting an input. So this is a concept of computing. Okay, so when do you say an input is accepted? So now let X be a input string, which is a string x1 to xn, where each xi is a symbol in the alphabet. We say that X is accepted by M if delta, so if the transition on this input, okay, so let me, so it's a start from Q0, that's the initial state, your input is X, and the transition, you determine your move, so let me give you some idea. Let's say we have X1, so this is X1. You go, now this is the initial state. So it's X1, then you look at X2, you go to the state. Now these states, some of these states may be the same as the earlier states, right? So right now we just drew this way because each state on an input, it will go to a state. So although the state may be the same, may already appear in the prefix, but this is what we will do. So finally, you go to xn, and that's a final state. Then we're saying that this X is accepted. So that's what this means. So that's what this, that is what this means. So if we want to describe it in using mathematical terms. So that means there are states R0, R1 up to Rn, such that R0 is the initial state Q0. Ri plus 1 is the next state from the current state Ri and the current input xi plus 1. Okay, so this is the Q0 current state on x1 current input. This is the next state, R1, okay? And finally, the last one is Rn. Rn is a accept state. So that's what this means. So then we put all strings that are accepted by this finite automaton into a set. And then we denote this set by L of M. And this L of M is a language. And this language is accepted by M. And we would call this, we call this language a regular language. So this is a regular language. Okay. So now let's look at an example. So now let's look at this state diagram. And this is also a in initial state and the final state is the same node. So Q0 is initial state, which is also a accept state. Okay, and the input you have is 0, 1, 2, and reset. Okay, so now let's go around to see what is happening. So if the input here is 0, it will remain the same. If it's reset, it will remain the same. That means reset means you go to the initial state. And if it is 1, then you go to Q1. From here, if it's still 0, if you read the next symbol you read is 0, you remain. If the next symbol you read is 2, you go back to Q0 or reset. So it looks like if you count the number of if you sum the digits, okay, so on your input string, if it's divisible by 3, then you will either accept it, okay, then you will accept it, right? Okay, for instance, if it's 1 and 2, 1 plus 2 is 3, then you accept it. Or if at any moment you have an input called reset, then you go to the initial state. All right. So then M actually accepts the following strings X. X either ends with reset, because if the reset, you go back to the initial state or accept it. Or the summation of the digits in X is divisible by 3. Okay, so now let's look at this one more time, right? So let's say your input is 1, and the next one is 1. Okay, 1 plus 1 is 2, so you remain in Q2. Okay, if the next symbol is 0, so you remain in Q2. Okay, if the next one is 1, then you accept it. So now, as you can see, we use this state to memorize the outcomes of summation. And then you divide by 3 to see what the remainder is. Okay, so this Q1 indicates the summation of the digits in your input divided by 3 has a remainder 1. In this state has a remainder 2. Okay, so in this state it's divisible. Okay, has a remainder 0. So that's, you can see here that we can use these states to memorize something. Okay. So once we know what a finite automaton is, and the next thing we would need to do is that how do we design a finite automaton? Okay, so languages that are accepted by an FA is called a regular language, as we said earlier. And then suppose you are given a description of a regular language. How do you design an FA to accept it? Okay, so that's our question. And of course, as we saw earlier, a state can be used to memorize something or certain features. So now the design technique is to use states to memorize certain features and think of yourself as an FA, okay? Place yourself in the position of an FA. So let's think of myself as an automaton. So this is probably easier to think of things. And I can use the states to memorize certain features. In other words, memorize what status I am in. So now let's use an example to demonstrate this idea. So we let L be a language of binary strings, okay, which means it's a string over this binary alphabet. And with an odd number of ones, okay? So in other words, this L over M this L over M is the following set of strings, okay, where the number of one, so this, first of all, X is a binary, so we can say this. X is a binary string, and the number of ones and the number of ones in X is odd, is an odd number. So that's L of M. Okay, so now, as we said here, we're going to use states. So here we have two states we need to memorize. So because when you count, you count the number ones in your input, it will either be an even number or an odd number. So you have two states, okay? So we use Q even to remember the former situation and use QR to remember the number ones is an odd number, okay? So at the beginning, when you have an empty string, that means you don't have either, so that is the initial state. So it is a zero number of, so when you sound the number, if you add the number of ones, because you don't have any ones, so that's zero. So that's your initial state. Obviously, this is what we want, so this is your final state. It is your add state, okay? I'm sorry, accept state. It is your accept state. So if you read zero, so the number ones is still remain the same, either even or, so it's still even. So if it's zero, then you remain the same. If it's one, from even, you add one, of course, you move to odd. Once you are in this state, if you read zero, it's not changed. But if you read one, then it's going to change, right? So this is a simple simple construction of this language. So let's look at another example. So in this case, let L be the language of binary strings that contain 001 as a substring. Okay, so now we use Q0, Q00, Q001 B states to remember what is read so far. That contains respectively 0, 0, 0, 0, 0, or 001 as substrings. Because for this, the substring could either be 0, prefix, right? It's the prefix, either 0 or 00 or 01. So let's do this as a prefix. Okay. And then we let Q be the initial state and Q001 be the final state. Once you have this, and no matter what you read afterwards, I'm going to accept it. Okay, once you read it. So that means now at the beginning, okay, if the input is 1, we're not going to change because you want only when you see 0, you're going to move to the next one. So when you see 0, you go to Q0 because now I have read Q, I have 0. If you read 1 again, then I cannot move on to the next because it breaks the pattern. So you go back, So, but if you are in Q0, which means I have read 0, and you read 0 for the new input, then you go to Q00. That indicates I have read 0 and 0, right? So if in this time I read 0, then I still have read 0 and 0, so I'm going to remain. If I read 1, that means I have read 001 because I am in this state. I know I have read 00. If I am reading 1, then I'm going to go to Q001. And then no matter what symbols you have, what inputs you have afterwards, I'm going to remain in this state because I have already read 001. I'm going to accept this state. Okay. So now let's look at what can we do about regular language. In other words, how can we manipulate regular languages? So we defined regular operations. So we have three regular operations at the language level. One is a union, the other one is concatenation, and the last one is called star in our textbook. And it is also known as clinic closure. Okay, so it is we have three operations on regular languages. So so now let A and B be two languages. We know what union is. Okay, so concatenation is just to put a string after another string. So let's say we use a circle to indicate concatenation. Sometimes we just remove that circle. Sometimes we just use A and B to indicate concatenation. Okay. So for instance, this XY here, we don't use a circle. We just say this Y concatenates after X. So XY. So in other words, you have a string X, and then you attach a string Y after X. That's concatenation. And clean star, we also call it clean star, okay? Or just star. A star, a set of, so A star is a set of X such that X is a string over A, okay? So in other words, you can break this X into substrings such that each substring is in A, is an element of A. Okay, but you also include, so let's say put it here, you also include empty string. It also includes empty string. Okay. So A star is a set of all finite strings over A, including the empty string, which corresponds to K0. So in other words, if K is 0, that means the length of X is 0. Of course, it can only be an empty string. Okay. Okay, then we can look at the following properties. So we let A and B be regular, then A union B is also regular. Okay, so now we are going to prove it. So we prove it by constructing a new finite automaton. Okay, so because A and B are regular, we know that there are finite automata MA and MB to accept A and B respectively. So let's call MA, which is a 5-tuple. QA is a set of states, sigma, they share the same alphabet. Delta A is the transition for MA. Q0A, okay, we indicate this is the initial state of MA, and this is the final state. Okay, so this MB is the same. We just change the changes A here to B with B. Okay, so A is accepted by MA and B is accepted by MB. So now we're going to construct a new FA. So in this case, for the union, I am going to take the new states as the Cartesian product of two of these two states, QA and QB. Sigma is the same. Delta is the one I'm going to define. The initial state is the corresponding initial state, right? The final state, the accept state will either so this is a cross. Okay, so this is cross. So this is not just simply union. So in other words, we want to know, we want to say one of the state is a final, then we accept it. So which means that it would be, so cross this. So cross that should be, if it's FA, so this is one of the state is a final, and then I don't care the next one because one of the, if one of the FA accepts the input, then we accept. So this means that FA accepts it. So I don't, this is B. Okay, or QA cross FB. So that's our final. That's our set of. That's our accept states. Okay, so I will make a correction on the slides for you guys. Okay, then the transition will be straightforward. So when So let's say your current state is P and Q pair. Your input is A, and then what you go is a delta A on PA and delta B on QA. Okay, so that will be your next move. And then of course, these machines obviously will accept the union of A and B. So in other words, one of the machines, so for any input, if one of these finite automata accepts it, then it accepts it. So that's what this means. So next time when we look at non-deterministic finite automata, we can come up with a simpler construction. So this construction is straightforward. So that means, okay, this theorem says the regular languages are closed under union. We can also show that regular languages are closed under concatenation and star, Kleene star. However, it's easier to do this proof when we look at non-deterministic finite automata. Okay, so it is convenient to first introduce non-deterministic FA and then show that FA is equivalent to NFA. Then we can use NFA to show that regular languages are closed under union, under concatenation, and under star. So that's why these three operations are called regular operations. Okay, so that is the end of this video.